In the previous video, I defined the terms stationary and non-stationary, and I listed several different features of a signal that can be stationary or non-stationary. In this video, I'm going to show several examples of non-stationary signals and their power spectra. This will help you understand the effects of different kinds of non-stationarities, in particular edge effects, and the results in the Fourier transform. Before getting started, it's important to make a clear distinction between the Fourier transform as a mathematical operation versus the results of a Fourier transform providing interesting or novel insights into characteristics of a signal. The Fourier transform is a perfect representation of the signal in the frequency domain. That means that no information is lost when going from the time domain to the frequency domain. On the other hand, the power spectrum obtained by the Fourier transform is not always so easy to interpret visually, and that is what I'm going to show you in this video. First, I'll start with a signal that is amplitude non-stationary. Here you see two signals. The red sine wave is amplitude stationary. The blue sine wave is frequency stationary, but the amplitude increases over time. Here are the power spectra from these two signals. The red line looks like what you would expect. There is zero amplitude at all frequencies except for the frequency that I simulated, 3 Hz, which you see here. Now this may seem strange at first because you see non-zero energy at frequencies that were not explicitly simulated in the data, and yet here they are. The reason why these are here is that the Fourier transform needs additional energy at other frequencies in order to capture these non-stationarities. Here is an example of a frequency non-stationary signal. This is a signal called a chirp, which increases in frequency over time. It's a bit difficult to see because the two sine waves are overlapping, so we can plot just the first one. Here you see the chirp signal. It's a sine wave. It's amplitude stationary, but the frequency of the sine wave is increasing over time. So this signal gets faster over time. In contrast, this red signal is both frequency stationary and amplitude stationary. And here you see the effects on the power spectrum. Again, the red line corresponding to the stationary signal looks like what you would expect it to look like. It has an amplitude of 1 and a frequency of 4. The blue amplitude spectrum, in contrast, has two features that seem to be surprising. One is that it's not really clear from looking at this amplitude spectrum what the signal should look like in the time domain. Secondly, the amplitudes are rather small. They seem to be approximately 0.1 across all these different frequencies. And yet we can see visually that the sine wave here has amplitude 1 all the way through. The next example will illustrate sharp transitions between stationary periods. So here we have a signal where each chunk of this signal is stationary. It's amplitude stationary and frequency stationary, but the transitions between these induce non-stationarities both in frequency and in amplitude. And here is the amplitude spectrum of this signal. And you can see that it has a lot of non-zero energy at all frequencies up to around 20 Hz or so. Nonetheless, you can still clearly see peaks in this spectrum corresponding to the 4 sine waves that were simulated in this signal. And that matches what you can read off of here. This next example may surprise you at first. Here we have a signal. It's just a regular sine wave at 10 Hz, but it's concatenated with the negative of a sine wave also at 10 Hz. So this part of the signal and this part of the signal are the same, except this one is reversed. It's just swapped. Now, this is exactly a signal at 10 Hz. There's no amplitude non-stationarities. There's no frequency non-stationarities. Everything in this signal is happening at 10 Hz. And yet, when you look in the amplitude spectrum, actually in this case I'm really computing the power spectrum, so when you look at the power spectrum, you see that the Fourier coefficient at 10 Hz is 0. Now this is quite surprising because the only frequency component in the signal is not present in the power spectrum. And what's happening here is that in the Fourier transform, we're trying to fit this signal with one single sine wave at 10 Hertz. But if you use one sine wave at 10 Hertz throughout the entire window of time, throughout the entire signal, the phases here cancel with the phases here. And that leads to Fourier coefficient of 0 at 10 Hertz. And again, this doesn't mean that there's anything wrong with the Fourier transform. The Fourier transform is doing exactly what it's supposed to do. It just means that because of this non-stationarity, the Fourier transform is not so easy to interpret visually. This next simulation illustrates an edge artifact. Oops, sorry, this should be time. There you go. So here we have a step function. It's a signal that is 0, and then it immediately turns into 1. And this has a rather funny looking amplitude spectrum with a negative decay, and it rapidly swaps between 0 coefficients and non-zero coefficients. Now the idea here is I'm going to uncomment this line and basically add a sine wave to this step function. And the question is whether this feature of the power spectrum resulting from this step function is going to overpower this sine wave and prevent us from being able to see this sine wave in the amplitude spectrum. So the answer is no. This coefficient just pops right out of the signal. It's linearly summed on top of the shape of the spectrum from the step function, and you can see that the amplitude is correctly reconstructed as 0.08. So the lesson here is that if you combine different features in the Fourier transform, those will sum linearly in the amplitude spectrum. Therefore, just having a non-stationary feature in your signal doesn't necessarily mean you're not able to detect stationary features in the signal as well. In this example, I created a large spike artifact in the time domain, and then we looked at the amplitude spectrum. In the next example, I'm going to reverse that and first create a power spectrum that contains all zeros and just a single one, and we'll get to see what that sharp wave looks like in the time domain when we take the inverse Fourier transform of this spike. So here's our response in the frequency domain, and here's all zeros, and I created just one spike here. And you can see that the inverse Fourier transform of this power spectrum, not surprisingly, is a sine wave. And this is kind of an interesting way to think about a sine wave. You can think of a sine wave as the time domain artifact of an impulse in the frequency domain. This is actually very important to keep in mind when you're studying filtering, bandpass filtering, and narrowband filtering, because if the shape of your filter in the frequency domain has very sharp edges like this, that can induce ringing in the time domain, which is an artifact. So in this video, I showed you that signal non-stationarities can make the power spectrum difficult to interpret. And this is not just some abstract theoretical quirk. Non-stationarities are present in all kinds of signals in nature and in biology. In fact, for many systems, the non-stationarities are of primary interest, and the stationary features of the signal are sometimes ignored because they are uninteresting. For example, without any non-stationarities, my voice would be just a monotonous tone. Music wouldn't exist either. And actually, neither would we. The brain needs non-stationarities in order to process stimuli and to produce thought and consciousness. So the difficulty of using the Fourier transform to understand non-stationary signals is a pretty serious limitation, because there can be important features of the signal that are difficult or impossible to ascertain when looking only at the power spectrum of an entire signal. In the next video, I'll show you a few common analysis methods for dealing with these kinds of non-stationarities and for understanding non-stationary signals.